For the last several days, we've been looking at the types of solutions we can have to various equations, and we discovered that we have a plethora of solutions to work with. We can have real solutions that could have rational numbers, irrational numbers, integers, counting numbers. We also can have complex numbers, things that are available on our imaginary number plane. And complex numbers often do have real numbers with them to make that pair. One part is real, one part is imaginary. Tying back to things that we looked about before with the graphs, especially when we said the quadratics, looking at solutions, we're looking to see where it's crossing the x-axis. Your x-intercepts, your roots, are representing your solutions. And so we know since it's a quadratic, we should have two solutions to be working with. So we could have two individual solutions. We could have one repeated solution. Remember, it's being used twice, once on the decreasing and once on the increasing interval. Or we could have some imaginary complex solutions. Those were the ones that were not crossing the x-axis, but we have a way to represent them with our values. We said we just have an imaginary axis that comes up from your real plane, and those complex numbers are located there. So here's some visuals. We said oftentimes people use colors to represent the values of complex numbers, and we can use that for different applications. And here's just some more examples with what the complex numbers look like and how color-coded patterns that they result and how we can use those for different options for the sequences to see how things belong. Lots of engineering examples here. So we've been working on solving different types of quadratic equations. And we have a method that we use when we're typically solving quadratics. So things that we want to ask ourselves, if we have a quadratic equation like we do here for number 5, 2x squared plus 8x equals negative 12, is it in standard form? Well, standard form should be the highest degree all the way down to the constant. So for us, this is not in standard form because the constant should be linked with the rest of the polynomial. So we're going to rewrite it in standard form. In order to do that, we'd have to add 12 to each side. So now this is in standard form, 2x squared plus 8x plus 12 equals 0. The next question we want to ask ourselves, well, is it factorable? So we're going to look to see if we have a greatest common factor, and I can see that here everything has a common factor of 2 on the left, so let's divide that out and see what we're looking at. Well, once we have that greatest common factor, we want to see, well, can we break down the interior portion? Can we factor this? So again, we have that product sum method that perhaps we can use, thinking about what times what gives us 6 and what plus what gives us 4. Unfortunately, there are no two factors of 6 that will multiply to give us 6 and add to give us 4. So we can't do this by factoring. Well, the other method we had available to us was solving by undoing. So remember, that's when we had a quantity squared equals a value. If the equation looked like that, we could definitely solve it by undoing. So the question is there a way that we could rewrite our equation to make it happen, that we could put it in that undoing format and solve like we normally do? Well, the answer is yes. If we can complete the square, that will make that happen. So what does that mean? We have to remember, well, what does a perfect square trinomial look like? A perfect square trinomial comes from a binomial squared. So x squared plus 6x plus 9 is an example of a perfect square trinomial because it came from the binomial x plus 3 squared. So when we take a further look, it's like, well, how are the two comparing to each other? How does the quantity x plus 3 squared relate to x squared plus 6x plus 9? Well, we have some patterns that do exist. If I look, the 6x came from 3x and 3x. Well, 3 was part of our binomial. We know 6 divided by 3 is 2. So this value ends up being half of that coefficient for the linear term. Well, is there another relationship with how we got the 9? Let's think. Where did the 9 come from? The 9 came from 3 times 3. So is that item times itself? So if we can use maybe these patterns by looking at to see what we have, maybe we can rewrite things in a completed square format to help us undo. So let's go and start taking some notes on this with number 5, picking up where we left off. We said write the equation in standard form, so we did that. So then we looked for that common factor and we said, well, it has a common factor of 2, so let's divide every single term of the polynomial in the equation by 2. So if I divide this by 2, I'll get x squared. If I divide this by 2, I'll get 4x. If I divide this by 2, I'll get 6. And 0 divided by 2 is still 0. So again, we're here, and we said we cannot factor this. So we want to try to write it as a completed square. So in order to complete the square, we're running into problems with this piece here. That was not making the square happen. So let's subtract 6 from each side. So now we've got x squared plus 4x plus something equals negative 6 plus something. This was the part that was missing and wasn't the correct value to complete the square. So if we think about how we did it before, we said the linear term coefficient, right? To make that perfect square binomial, we need to know half of its value. Well, what's half of 4? That's 2. So 2 would go in our binomial. So let's remember that when we're multiplying the binomial, it's x plus 2 times x plus 2. So we've got that half. This number here came from that number times itself. Well, 2 times 2 is 4. So we're putting a 4 here to complete our square. Well, if I'm adding a 4 to the left-hand side, I have to add 4 to the right-hand side. So we're going to have our negative 6 plus 4. Well, we've completed the square on the left. There's our binomial squared. So on the right, we're going to simplify this. Negative 6 plus 4, that's negative 2. So here is our format. It's in undoing form. So like we did before, to undo this, we had to get the binomial by itself. If something is squared, we take the square root of each side. So we're going to square root each side of our equation. We know the square root of something squared is the absolute value, and then we have it equal to the square root of negative 2. Well, right here, the square root of negative 2, we know we can simplify that even more. We can simplify that as the square root of 2 times the square root of negative 1. We can't simplify the square root of 2 because it has no perfect square factors, but we do know the square root of negative 1 is equal to I. So I can rewrite that as I times the square root of 2. This is the distance they want us to travel from our 0. And that's in our complex number plane, so we can go this distance left and right from where we started. Remember, denoting going to the left, you have negative 1 times where you started equals your distance. Going to the right, 1 times where you started equals your distance. And you undo them accordingly. So here on the left, I would divide each side by negative 1. On the right, I would divide each side by 1. So on the left, I'd have x plus 2 equals negative I times the square root of 2. On the right, I have x plus 2 equals I times the square root of 2. We're still trying to get x alone. Well, we have to undo this addition of 2, so we'll subtract 2 from each side. So that leaves me with, on the left, x equals negative 2 minus I times the square root of 2. And on the right, x equals negative 2 plus I square root of 2. Notice how they have the same real number value, negative 2, but the complex number value, we're going to the left I square root of 2 and to the right I square root of 2. Again, we talked about how mathematicians like to condense things, so you could write the two answers as one expression. Negative 2 going to the right and left, I square root of 2. So let's take a look at another one. Here we have 3x squared plus 8x equals 35. So again, as we're solving our quadratic equations, things we want to ask ourselves. 1, is it in standard form? So remember, it's got to go from the highest degree to the constant. We can see we've got our quadratic or linear. Our constant should be here. So since this is equal to 35, that's not in its standard format. We want to move that to the other side. So if I subtract 35 from each side, I can put it into standard form. The next question you want to ask yourself, well, is it factorable? Does it have a greatest common factor that we can divide out from every single term? No. Can you use your product sum method to help you do some factoring? Well, we'd have to take the leading coefficient times the constant, so we'd have a negative 105, and then we need to add to get 8. And so we're not able to find the factors for those. So factoring is not helping us do those. Can we solve it by undoing? So can we take that equation and put it in the undoing format? So we typically take the leading coefficient and divide every piece in the equation by it to see what we have. If I do that, I would have this. So in order to complete the square, again, we're supposed to take, where the problem is for the square is this constant term now has to move to the right-hand side. And so we're going to take half of our linear coefficient term. Well, half of 8/3, that would be 8/6. And then we'd have to take 8/6 times itself and put that value here and add that value to our 35/3 here. And we can do that, but we're getting into some more complicated fractions and it's just getting more involved. So the question is, if we don't want to try completing the square, is there another method we could utilize to solve this quadratic equation? If it's not good for factoring, it's not good for undoing, it's not good by completing the square, what else can we do? And we do have another method, it's your quadratic formula, and you probably have utilized this in the past. Your quadratic formula states that as long as your equation is in standard form, and that's equal to 0, and the coefficients for the quadratic, linear, and the constant are all real numbers, we can substitute the coefficients of those values into our formula and calculate according to our order of operations to get our two potential solutions for the equation. So we already talked about putting the equation in standard form. So now at this point, we just have to identify our coefficient values for A, B, and C. So our coefficient A is in front of our quadratic term, which is 3. The coefficient for B is in front of our linear term, which is 8. And our value for C is -35. We take those values and substitute them into their locations for the formula. This will not change. All of those stay in place, and this is something that you should memorize and help you with your solving process. If I substitute my values into the formula, again, all we have to do is implement the order of operations to simplify it. So I would probably want to start with inside my radical here, and I know 8 squared, 8 times 8 is 64. Then I would want to simplify the multiplication here. So again, multiply 2 items at a time. -4 times 3, that's -12. Then you have a -12 times a -35. That would then be a positive value. Here we've got 2 times 3 in the denominator, which is 6. And we know the opposite of 8 is -8. So we have all the pieces that we need. Again, we just continue to simplify according to order of operations. So here, simplifying underneath our grouping symbol, we're going to add the 64 to the 420. And next step is to actually say, well, is this a value? So 484, does it have any perfect squares, or is it a perfect square itself? And if you look at your table for your perfect squares, 484 is 1, and the square root of 484 is 22. So here we're simplifying even more. We've talked about solving the quadratics, and the idea about left and right came up with undoing. And look, here's your left, your negative, here's your right, your positive. So setting them up in the 2, going to the left and going to the right to help us simplify for those values are helpful. So again, we just have to simplify the numerator and then divide it by the denominator if we can. So we know -8 minus 22, that would be -30. We have -8 and a positive 22, that would give me 14. So we just have to do the division part. So -30 divided by 6. Well, there's a common factor of 6 here, so x should equal -5. 14 and 6, they both have a common factor of 2, so that could simplify to 7/3. So here we have two real solutions, x equals -5 and x equals 7/3 for our quadratic. We could check these solutions like all the others by taking one at a time and substituting it back into the original equation. So if I put that -5 into the left-hand side, I should get back my 35. If I put my 7/3 in for x, what I have on the left-hand side should match my 35 on the right. So now we have 4 methods that we could use for solving quadratic equations. We began by undoing them, So remember, having a binomial squared, getting that distance, going left and right, and simplifying accordingly. We've done it by factoring, looking to see if it's got a greatest common factor. Can use your product sum, take each factor, set them equal to 0, and solve. We do have our quadratic formula, so putting it into standard form, identifying your values for A, B, and C, substituting it to the formula, going left and right to get your two results. And we also have completing the square. So looking to see, is it in standard form, any greatest common factors to divide out, trying to complete the square. So the constant is what was the problem, subtracting it to the other side, seeing what we needed to make it true. So taking half of the linear term, multiplying it by itself, just make sure whatever you're adding to this side, you're keeping it balanced to the other. Then it's in the undoing formats. You're implementing all the skills and resources that you had before with the original method to get your two solutions. We can have real solutions, we can have complex solutions. It all depends on the function that's given to us. So in our next lesson, we'll do some more practice with solving by completing the square, solving with your quadratic formula, and seeing when we could apply each of these four methods based on the quadratic that we're given.